term. For the from 5:10 p.m. to say 3 hours, 2.5 hours, 150 minutes. Okay, long term. Okay, any problem? No? No problem. I will put in our lab too. The homework number 6, this is a series of the problems to train you how to do a simple real problem. This is just a like a PMD system or a ABA system, and ask you to convert it from the this second order equation to the first order state space model, and also ask you to convert it to discrete time state space model. There's a function file in SCI lab. I forgot the name now, but I can put in the web, or the assistant can put in the lab, that allow you to transform from continuous time state space model to discrete time state space model. So you do not have to program by yourself. However, you are welcome to program by yourself to verify your concept in your brain. All right? And then I ask you to perform simulation for 1,000 sample points with the input accelerations. That is just a function to drive your system. That's AG. That's like an earthquake, forcing the functions. This is easy problem. And also, by the way, I will give you all the solutions from problem number 1 to problem number 5, maybe sometime this week or next week, because the teaching assistant is busy in doing his thesis. But I ask him to do it before the end of the week, that you have all the solutions before the big term. Sounds good? Any questions you have? Some students ask about the damping ratio. The damping ratio is really defined in this page 10 in the response of dynamic system. This is a damping factor. The damping factor is the damping ratio I'm talking about. I should let you know earlier. Have any problem on this? For any system, the damping ratio, the zeta n. This zeta n, you see the zeta n here?
In the homework 5.
In the homework 5. Yes. So you have to convert. See, this zeta is for this zeta. So if you know this zeta n, say 0.05, you know n, you know omega n, and then you can compute this zeta, right? Understand now? This is your equations. Agree? That's your equations. Now, if you know m, you know k, then you know omega n. That is omega n here. Because you know n, you know this zeta n is 0.05, right? So this zeta equal to 2 times m times omega n times zeta n.
Yeah, right now, case we have a trivial freedom. So what's the closed loop?
Oh, yeah, you ask it here, there's more than one degree of freedom, right? I'm talking about the systems to have, the important sense is to system to have this 0.05. Although when you sub this number into your, they pull out the number 5, where's number 5? And I can explain to you number 5. Okay, let's talk about number 5. That's an important concept here. Okay, let's see. You have a number 5 here. Number 5 here. That's number 5. I'm talking about select this data C such that this data is known, right? This data is known. That data, that's for the real system. But I'm talking about a closed loop system. So you are to go to for this problem, you need to what you need to do is you need to try this data n is MC2 MC. Okay. Data C. That's a good question. What you need to do here is you need to try many different data C, maybe plot a curve, the data C, all right, and plot a curve, and then you check your cross loop, your cross loop, the system, the eigenvalues, and that's cross loop eigenvalues, and then that will be different from this, right? So you need to check your closed loop system eigenvalues such that your closed loop eigenvalue, the damping is more than 0.05. Your closed loop eigenvalue will have 2 eigenvalues for this system. And I'm asking you to have both of them more than 0.05. Both of them. The closed loop eigenvalue, you have 2 eigenvalues. So you can plot eigenvalue. Eigenvalue 1, what is the damping ratio for that? Number 2, what is damping ratio for that? And then you choose the data C such that both eigenvalues have 0.05 damping ratio. Understand? So you have eigenvalue. Let's see how can you make sure your eigenvalue have, you go back here, the damping ratio. Now, you need to go to solve like this. Omega n, like, well, because it's 2 eigenvalues, both eigenvalues, you can write the eigenvalue number 1 and eigenvalue number 2, and both have its own the eigenvalues. And how can you make sure your eigenvalue has the data n like this? And that is 0.05. Go home and try, right? You didn't do it right, you go home and revise it and resubmit. How about that? Huh? Okay?
So we can resubmit the
Yeah, you can resubmit it. Yeah. So go do the exercise and resubmit. I just try to have, you may not be able to achieve that. By the way. It's not always possible to do that. I'm asking to see if this the homework number 5, can you do that? Select the such that the closed loop, as a closed loop system damping ratio is 0.05 both eigenvalues. And then you will see that out. That's what we call damping ratios. And we look at the damping ratio for both eigenvalues, and this is the one, this is the formula you need to figure out. That's the formula. Now, so